video, we are going to discuss about a concept in polynomial theory, that is redivision in the polynomials. Okay, and after that we will discuss about a very important theorem, that is remainder theorem. So let us see one by one. Okay, so in case of numbers, we know that if we are given two numbers and one is positive, if suppose we will divide two numbers, if we divide 15, so if we divide 15 by 6, what we will get? We will get 15 equals to 6 into 2 plus 3, right? So here we are getting a quotient and a remainder, right? And so we are dividing 15 by 6, and there is something to notice, that 3 is less than 6 but greater than or equals to 0. Okay, so these are known from our concepts in number theory, right? So we will see that in case of polynomials, this same concept is also valid. Likewise, we can perform division in polynomials. Okay, let us see an example. So if we divide 2x cubed plus x square plus x by x, we will get another polynomial, that 2x square plus x plus 1. So we can say that we can take common x from 2x cubed plus x square plus x, and we will write it as x into 2x square plus x plus 1. So we say that x and 2x square plus x plus 1 are factors of these polynomials. Okay, but suppose if we are given that x square plus 2x plus 3, and if we try to divide it by x, we get x plus 2 plus 3 by x. This is not a polynomial, right? This is not a polynomial. So x is, we cannot write it as product of two polynomials, one that x square plus 2x plus 3 equals to x into another polynomial qx, such that qx is a polynomial, because here we can see that x to the power minus 1 is present, right? So we cannot divide x square plus 2x plus 3 by x. Okay, all right. So in the next concept, we will see that, the same thing, that if we divide 3x square plus x plus 1 by x, we cannot get a polynomial. So x cannot be a factor. Okay. Now we will see how to divide a polynomial by a systematic process. So here we will go through the example 6. So in our example, the polynomial is px is x plus 3x square minus 1, and gx is 1 plus x. We have to divide px by gx. So let it go. So px is p of x and g of x. Okay, p of x is x plus 3x square minus 1, x plus 3x square minus 1, and g of x is 1 minus x. Am I correct? 1 plus x, sorry. So this is 1 plus x. Okay, so we will see how to perform a systematic division process. Okay, so we will write x plus 1 here, that is gx, and we will write 3x square plus x minus 1 here, and we will see. Okay, so what have I done? I have written this polynomial p of x here in a proper order. Proper order means I have written it in a descending order, that is descending order of degrees, that is 3x square plus x minus 1. In each term the degree is descending, and in case of gx also I have written in that order. So this is our first step to follow, that we have to write px and gx in our proper order. Okay, so what we will do, we will divide this first term by the highest term here, that is x, and what we will get, we will get 3x, right? So we will put 3x here. So while multiplying with 3x into x plus 1, we will get 3x square plus 3x, and we will subtract it, and what we will get, we will get minus 2x minus 1. See how long we can perform this thing. That long, the first term will be divided by the highest degree term of the polynomial by which we are dividing, right? So what we can get while dividing minus 2x by x, we will get minus 2. So what we are getting, that is minus 2x plus minus 2, right? So we are subtracting it again, and we are getting that plus 1. We cannot divide 1 by x, so we cannot proceed further. Okay, so what can we write? That we can write 3x square plus x minus 1 equals to x plus 1 into quotient, that is 3x minus 2 plus remainder, that is 1. Here one thing is to observe, that degree of the remainder is always less than the degree of the polynomial by which we are dividing, right? So degree of remainder Rx is always less than degree of Gx, the polynomial we are dividing. If the degree will be equal to or greater than equal to, we can perform this step, this procedure, what we have written here in this way. That procedure would follow once more, right? So degree of Rx will be always less than degree of Gx, and it will greater than 0. This is a possibility, and another possibility is Rx is 0. Mind it that Rx equals to z. If Rx equals to 0, then Rx has no degree, right? So okay, degree of Rx can be equals to 0 also. If in this case here the remainder is 1, which is a non-zero constant polynomial, so its degree is 0. Okay, yeah. So what we are getting? We are getting this formula, that dividend equals to divisor into quotient plus remainder, which is also true in case of numbers. That thing is also true in case of polynomials. The thing is to note that these all things, quotient, remainder, all things are polynomial. Okay, yeah. So this is our formula. If P is the dividend and G is the divisor, then we get this formula, that Px equals to Gx into Qx plus Rx. We get Qx, that is quotient and remainder, uniquely. And the what is the condition of the remainder? That remainder, degree of the remainder is less than degree of gx and or rx equals to 0. Which one? I have written it in the slide. That is this one. This one. Okay, so px, which is divisor, sorry, dividend equals to gx, which is divisor into quotient plus rx, remainder. This is quotient. Okay, and this condition holds. So we have learned the concept of division in polynomials. Okay, so now one thing, if we divide, that means divisor is of degree 1, then we get a remarkable theorem which is known as remainder theorem. Suppose px be any polynomial of degree greater than or equals to 1 and a be any real number. If we divide px by a linear polynomial, that is polynomial of degree 1, then we can determine what our remainder will be. That remainder will be p of a. This is our statement. That means if we divide px by a 1 degree polynomial, that is linear polynomial x minus a, then we get qx plus rx, and we can determine this rx as in terms of p of a. We don't know what our rx is, but due to this theorem, but we know about px. Px is given to us, x minus a is given to us. We don't know about rx. What we want to know? We want to know about the remainder, and we can get it by simply putting a in place of x, and that is p of a is the remainder. This is by virtue of the remainder theorem. Right? Yeah. So what is the proof? Our proof follows in this way, that suppose we know that we always find a qx quotient and a remainder rx such that px equals to x minus a into qx plus rx degree of rx. Okay. So degree of rx is always less than degree of divisor, that is x minus a, that is degree of x minus a is 1. So rx equals to 0, or rx is a constant polynomial, non-zero constant polynomial. One of them will hold true. Okay. So for every value of x, okay, right? So what can we do next? We can put a in place of x, and what we will get? We get pa equals to a minus a into qa plus rx, which is a constant, that is pa equals to r. So we are getting the remainder is p of a. This p of a can be 0 or some other constant, but it is a constant, getting replacing x by a in place of px. Okay, so we are getting so our remainder theorem is proved. Okay, so remainder theorem.